Thank you very much for a very nice talk. And I completely agree with the new idea of the multiple different kind of accelerator chiplet makes a very good and 360-degree solution of the, not just for AI, but anything. And actually, the past 5 years, we also worked for some multi-hetero accelerator solution with what we did is not a chiplet, but more a higher level with a GPU and FPGA working together. And in our experiment, the most important and hard problem is how to develop the software. So that it is quite relatively easy to make the multiple chiplet or any. In our case, we just put everything in the PCI Express, the common bus, and so that we made some couple of the very successful application mainly for the HPC. But the problem is that especially for the FPGA programming, it's so hard for the application users. And perhaps you not just think about open everything in the application level, but in some system software developers. But still, the problem is the language and accelerator communications. What kind of a layer you provide? So, what is your good software solution to make a good balance of the hardware and software?
Yeah, this is an excellent question. First of all, and I agree, I focus today because my research is focused on system on chip and the heterogeneity in the system on chip. You can integrate in the system on chip GPUs, which actually is one of the things we are progressing towards because there is a good open source hardware GPU now. But the type of heterogeneity that you're talking about in the system, meaning at a little bit higher level where you have GPUs, FPGA on the PCIe bus in a larger scale system, that also is very important, makes sense. And it's common, I agree with you, it's common that across different systems at different scales, software plays a key role. I focus a lot on hardware today, but hardware together with verification and software, these are really the three important aspects of building a complete system. And we all know that there have been chips that have been designed that are very difficult to program and therefore they're not going to be very successful. So there are these are fairly complex topics, but we we focus on SoC and we made it simpler to a few things, to integrate many different accelerators with a correct by construction type of approach in terms of functionality. We make it much easier to go on FPGAs and test your complete system, running application on top of the operating system, invoking these accelerators. When I say easier, I mean that, for instance, I teach a course in the fall semester at Columbia, where I start in September, where students don't have necessarily been exposed to FPGAs or to certain aspect of hardware-software integration in the context accelerator. By the end of the semester, all of them are able to develop an accelerator integrated on SoC, on FPGA, a small SoC, maybe a 2x2 or 3x3, and test some application. Did I solve all the problems? No. So what are the API I show you when it comes to invoking accelerator based on device drivers? It's a fairly simple API. So if you are good at programming in C, C++, and you want to offload a few important computation-intensive tasks to accelerators, that I would say is fairly easy. The second example I gave you with the one of HLS, based on HLS for ML, where if you are developing an accelerator for inference on the edge using this infrastructure, that's also very easy. But a lot of research remains to be done if you want to have legacy code for a different type of application programming languages, and there are open questions with respect to compiler and mapping. So I'm not claiming that I've solved all the software aspects, but our chip was fairly easy to program, that for sure.
Yeah, so that one of the common language base is SYCL, I think. SYCL, SYCL.
SYCL.
But there now, I'm really doubtful about the future of the SYCL, and even Intel is not so interested into that. So how do you feel about SYCL or such kind of the multi-platform common language?
Yeah, so
your solution?
I don't have I would say I don't have a strong opinion to give on that. What I'm going to probably answer in a different way. I'm saying that in the way I see it, system will become more heterogeneous at every level. There will be more specialization. It's difficult to know in advance which programming languages will win. In terms of languages to integrate intermediate representation, there are some good candidates that people are thinking about. But raising the level of abstraction there is key, because right now in ESP, for instance, everything ultimately gets integrated at the register transfer level. But it's a fairly low level of abstraction if you want to simulate things. And so this is why also we prototype a lot. In terms of one final thought, in a world where there is more domain-specific application, emphasis on domain-specific application and so forth, developing, probably we're going to need domain-specific languages and paths from software to hardware from those. And so I gave an example of one of them, but certainly there is work to be done to develop others. And there is work that goes beyond chip design, of course, goes to system software and compilers. Okay. So it's a rich agenda. But, now we have even more powerful tools. So.
Okay. Thank you.
Do we have any other questions? Yes, Jess.
So this might be the dumb senior manager question, Luca. Really enjoyed your talk. I guess I'm thinking from the perspective of, we're running our seismic network here in New Zealand and thinking about these kind of system on a chip things for being out in the field and doing ML for live processing of events and things like that. My question to you is with these kind of techniques and frameworks that you've got here, how does that change the kind of capabilities we should be looking for from our development teams that are building these systems for in the field? Should we be looking for some kind of, rather than having to know the entire stack, are we looking for key capabilities to kind of make that work really well?
That's a pretty important question. And and I guess also it depends on ultimately which type of chip you are doing. Not in the sense of, I could answer quickly by telling you, with essentially eight PhD students, one of them with a lot of experience in chip design, but only one essentially, we did that chip in a few months. But that chip is not a product, and is a vehicle to demonstrate research ideas. It works. I'm confident that based on that chip, we could build other chips which don't just demonstrate research ideas, but for certain fields could be the final implementation. There are some of the people that are using ESP right now. They essentially are a research group in industry that they test ideas, also in government labs to develop. Because similar to the previous talk, you need to develop specialized hardware. One thing is to do it with FPGA, but sometimes FPGA doesn't cut it, either because you need more energy efficiency or reduce the cost. And some people go for designing chips increasingly. And in fact, these people are very interested in using ESP because it reduces the cost. So those teams, my understanding as of now, that whenever you tape out a chip, you need still somebody who knows what we refer to as physical design. Go through from RTL, Verlo VHDL, all the way to the tape out. Now, only one person who coordinates a team that may be, but I can tell you that when we did Epox 1, essentially the team had, you could say, two leaders. One who was more the architect leader, going from make it happen what the professor and the other PI were saying in terms of the architecture, choice of the various component implementation, configuring of the NUC, all the way. And the other one was the tape-out leader, taking the RTL and bringing it to physical design. And of course, you need to have a dialogue between those two because, if you want to do this on a time. So I would say that is the case. And I think maybe my answer is that you need a team with an heterogeneous set of skills. They collaboratively work together.
Jason, do you have a microphone there?
So to be clear, this architecture can take you from designing in the FPGA, you can instantiate an ESP grid, and then on an FPGA that you've already got laying around. The framework is there to allow you to create a tiled design.
Yeah.
And
so
then
with
from
ESP, from the graphical user interface, I could claim, when it comes to FPGA prototyping, if you give me a little bit of slack, I could claim that it's push button.
Cool.
Let me tell you this, I didn't have time to explain this, but our students basically remotely configure the FPGAs from the graphical user interface and test it and get the result. Now, this is different from saying push button to tape out. That's not push button. Taking to tape out of a chip.
Yeah,
but
yeah.
on the prototyping FPGA,
Yeah,
yes.
I mean, if your endpoint is FPGA design, then it's, as you say, push button.
Yeah.
Right.
And do we have another question? If not, please join me. Thank you.